My name is Aryeman Singh, and welcome to Physics Lab 4, where we talk about string physics. Today's purpose is to demonstrate the practical application of physics principles by looking at the periodic motion of a spring in the frame of the conservation of energy. We're going to validate kinetic energy, potential energy, and the energy principle. And so our basic formulas for today's experiment are the net force, the sum of forces, our F net is dp dt, the spring force and this potential energy of a spring is 1/2 k times the difference from the equilibrium and current length squared. K equals 1/2 mv squared is our kinetic energy formula. The potential energy of gravity is mg delta h. And the energy principle itself is that the change in the system equals the work of the surroundings. And because our system is going to be the spring, gravity to the earth, and and kinetic energy, since we're incorporating all that into our system, our change in energy is going to be 0. So kinetic energy plus the change in kinetic energy plus the change in potential energy plus the change in the spring will be 0. Then we'll use some basic position update and velocity update formulas, and that is basically it. So a brief preview of our experiment is that we'll look at the modeling of our spring while it's moving on the x and y axis, and we can see some distinctions, and we'll go over that in a second. Spring. So we take the ball mass to be 0.402 kilograms and its initial position to be negative 0.118 and negative 0.616 on the coordinate axis, with our fixed point being at the top. And our initial velocity is just 0 because it hasn't moved yet. And so we take our g to be 9.8, so that's our acceleration of gravity. Our spring constant is 6.83, which is calculated with the period equation, and which is t equals 2 pi square root of k over w, or w over k, and where w is our omega, which is the angular velocity. And then you have L equals ball dot position minus spring dot position, and so we're just calculating the spring vector, and that way we'll calculate the kinetic energy with 1/2 mv squared, and then our potential energy by gravity, which is mgh, and then also by spring, which is 1/2 ks squared. And then we have our total energy, which is k plus ug plus us, which just equals our total energy, and then our E minus EI, so our delta K, delta UG, delta US will all just be the final minus initial, and we just recalculate that with our updated velocity with the position update and velocity update formulas, and then we can take the force of the spring and force of gravity to help calculate those two changes as well. And then we can put those together and create a model, which we will look at just now. Observe that we have a model and experiment version on the x-axis, and we can see that it's pretty similar, and that there's not much variation besides in the periods. So the periods are a bit off, but the overall minimum and maximum are pretty similar. So in the x direction it was fine. The y direction it's a bit more off. You can see that the minimum and maximum values are a bit different, and so are the periods. This could be caused due to a bunch of different errors, but it shows that the model and the experiment how they account for different factors. The experiment accounts for drag and stuff like that, whereas the model just accounts for the spring force, gravity, and the kinetic energy of the spring itself. So the error could have come from a bunch of different areas, mostly probably the calibration stick, and then also errors in determining the point for the mass. Also the inaccurate spring constant and friction and drag. These 4 factors could have affected the end result in the model. And so what does it mean? Is the energy principle conserved? Well, or satisfied? And yes, it is. We can see that from our final graph of delta K, delta UG, and delta E and delta U spring, it should be 0. And that is the case, as we can see in the orange line. So thus, change in energy of the system equals work of surroundings, which is 0 since everything is in the system. And thus energy is conserved in the system. Finally, so the period for x. So what does it mean by time when it comes to time period? Well, our average time period is 1.66 seconds on the x-axis, and on the y-axis it's 1.77 seconds. And so the causes for these differences could be because the k was calculated using the y period, so the x period will be a bit different. We don't have a k for the x period as well. So we could adjust this by distinguishing the equations, having one equation for the x period k constant and one for the y period k constant. And that way we could have 2 different periods that are more accurate and align more. Thank you.